Ever felt like a chemistry textbook is, I don't know, less a friendly guide and more just a dense jungle? All those unfamiliar terms, endless
Oh,
reactions.
absolutely, yeah. You stare at the page and wonder if there's a way to actually get it, not just memorize facts.
Exactly. And that's kind of our mission today. Welcome to the deep dive.
We're tackling part two, the elements and their compounds, from Shriver and Atkins Inorganic Chemistry, the fifth edition.
And the goal is really to cut through that dense feeling, right? Give you a shortcut to the core ideas.
Precisely. Show you how all that seemingly overwhelming information actually fits together. It forms this, well, this beautiful rational tapestry of patterns.
Yeah, the book actually promises that, doesn't it? It says this section reveals a rich tapestry of patterns and trends.
And crucially, that these can all be rationalized and explained by fundamental concepts, things you probably already know deep down.
So think of us as guides, maybe, helping you see the connections, the surprising insights, even without diagrams in front of you.
Exactly. We'll walk through how the book systematically describes element properties and reactions across the periodic table. You'll see how predictable it can be once you grasp the basics.
Okay, I'm ready. Let's dive in. Chapter 9 sounds like the foundation, laying out the periodic table's blueprint.
It really is. It starts with the fundamental atomic characteristics that control chemical behavior. First up, atomic and ionic radii, size basically.
Okay, size. How does that vary?
So generally atoms get smaller as you go across a period, left to right.
Why is that?
Well, the nuclear charge is increasing, pulling those outer electrons in tighter.
Mm-hmm.
But as you go down a group, top to bottom,
They get bigger.
consistently bigger, yeah. You're adding whole new electron shells. So the atom itself just expands outwards. And this size difference, it directly impacts reactivity, you see.
Okay, that makes intuitive sense. Bigger atoms, maybe electrons are easier to lose. Which brings us to ionization energies.
Spot on. Ionization energy is just the energy needed to remove an electron from a gaseous atom. Low energy means it's easy to lose an electron, form a positive ion, a cation.
And that trends across the table, too.
It does. Generally increases across a period, those electrons are held tighter, remember.
Right. Higher nuclear charge.
Exactly. And it decreases down a group because the outermost electron is further away, shielded by inner electrons, much easier to pluck off.
So, big atom, low ionization energy. Makes sense.
It does. And that connects to another term, enthalpies of atomization.
Okay, what's that measure?
That's the energy you need to take a bulk element, like a chunk of metal, and break it up into individual separate gaseous atoms.
Ah, breaking all the bonds holding it together.
Precisely. And the book highlights a key trend. This enthalpy generally increases as you have more valence electrons involved in bonding. Think lithium versus carbon.
So carbon, with more valence electrons, has stronger bonds holding the solid together.
Much stronger bonds, yeah. Takes more energy to break it down into individual atoms compared to, say, lithium.
This is great, connecting these fundamental numbers to actual properties, like metallic character. How does that fit in?
It fits perfectly. Metallic character generally decreases across a period and increases down a group.
Okay.
And you can link it straight back to ionization energy. Low ionization energy.
Yeah.
Easier to lose electrons.
More likely to be a metal, that electron C model.
Exactly. They readily give up electrons to form that C, allowing conductivity and all those metallic properties.
But the P block you mentioned, that gets a bit more interesting. Allotropes.
Ah, yes, the P block. It's fascinating. Many elements there can exist in different structural forms called allotropes. Sometimes the same element can be a metal and a nonmetal, depending on the allotrope.
Wait, really? Like the same element?
Yeah. Take arsenic in group 15. It has a yellow non-metallic form. It also has a gray sort of semi-metallic form, and even a black metallic form.
Wow. So it's not a sharp cutoff. The element itself can wear different hats, structurally speaking.
That's a good way to put it. It's about how the atoms arrange themselves.
That's genuinely wild. Okay, let's talk stable oxidation states. How do electron configurations drive these?
Electron configurations are absolutely key. Atoms want to achieve stability, often like a noble gas. So in these S block, group 1 elements, they lose 1 electron, boom, plus 1 state.
Easy. Group 2.
Lose 2 electrons, plus 2 state. Very straightforward.
No.
Just losing those valence electrons.
Makes sense. But the P block again, feels like there's always a twist there.
There often is. Groups 14 to 17, they can gain electrons to complete their octet, giving negative states like -4 and -1.
Right, like in non-metal compounds.
Exactly. But they also show positive oxidation states, sometimes up to their group number. And here's where we find a really important recurring theme, especially for the heavier elements. The inert pair effect.
The inert pair effect. Okay, what does that mean? Sounds like some electrons are being lazy.
Sort of. It means there's an increased stability for an oxidation state that is 2 less than the group oxidation number.
Two less. Example.
Think thallium, TL out, down to group 13. The group state is +3, but thallium really often prefers +1.
So it only loses one p electron, not the two s electrons as well.
That's the idea. Those two Ns2 electrons, the inert pair, become surprisingly resistant to being removed or involved in bonding for heavier elements. Its complex relativistic effects played a role, making them more tightly bound. Plus, sometimes the energy gained by forming 2 more bonds just isn't worth it because the bonds are weaker with larger atoms.
So those ns2 electrons are just kind of stubborn.
Stubborn is a good word for it. It explains why TLI is common, not just TLI. Now, moving over to the D block.
The transition metals.
Right. Their maximum oxidation state often matches their group number, especially up to around group 7 or 8. Manganese in group 7, for instance, hits +7 in permanganate, MnO4, that deep purple ion.
Oh, okay.
But after you pass the halfway point, the D5 configuration, that tendency weakens, and lower oxidation states become more common.
An electron spin, does that play a role in stability?
A big one. The book points out that half-filled and full subshells are favored, and also that having parallel spins is stable. Think spin correlation.
Okay. Like electrons prefer their own space.
Kind of, yeah. They fill orbitals singly first with parallel spins before pairing up. This minimizes repulsion. It leads to specific stable states. Like manganese, again, it's 3d5 4s 2. When it forms Mn2, it loses the 4s electrons and gets that super stable half-filled 3d5 configuration.
Ah, so that's why Mn2 is so common.
Exactly. Much more common than M3, for example. It's all about achieving that stable electron arrangement.
Fascinating how these electron details dictate so much. Okay, let's journey through some specific elements now, starting right at the beginning. Hydrogen. The book calls it the chameleon element.
And it really is. Just one is one, so simple, but its chemistry is incredibly diverse. It can lose that electron, become H plus a proton, a strong Lewis acid.
Or gain one.
Or gain one to become H, the hydride ion, which has 2 electrons and acts as a strong Lewis base. That range is unique.
And it's involved in, well, arguably the most important interaction for life.
Absolutely, hydrogen bonding. That interaction where a hydrogen atom acts as a bridge between 2 highly electronegative atoms, like oxygen or nitrogen.
The reason water is liquid.
Pretty much. It's the glue holding water molecules together. But it's also fundamental in biology shaping proteins, holding DNA strands together. Its importance is just immense.
Such a tiny atom, such a huge impact. How does it bond with other elements? The book mentions different types of hydrides.
Yes, it categorizes them nicely. First, you have molecular hydrides. These are formed with p-block elements that are similarly or more electronegative.
Like methane, water.
Exactly. Methane, CH4, ammonia, NH3, water, H2O. They form discrete molecules with covalent bonds.
Okay, covalent. What's next?
Second, saline hydrides, sometimes called ionic hydrides. These form with really electropositive elements, the alkali and alkaline earth metals mostly.
Like sodium hydride, NaH.
Perfect example. Here, hydrogen actually gains an electron to form the H ion. So you get an ionic solid structure like NaCl.
Ionic, okay. And the third type?
Third is metallic hydrides. These form with many D-block and F-block metals. They're often non-stoichiometric, meaning the H to metal ratio isn't fixed whole numbers.
More like an alloy.
Kind of, yeah. Hydrogen atoms tuck into the spaces within the metal lattice. Their properties are quite different, often retaining metallic characteristics.
Hydrogen's obviously huge practically too, especially with clean energy discussions.
Yeah.
How is it typically made?
Well, industrially, the main method is still steam reforming of natural gas. But there's a big push for greener methods.
Like electrolysis.
Exactly. Electrolysis, splitting water using electricity. If that electricity comes from renewables, like solar or wind, then the hydrogen is green.
Makes sense.
And there are even more advanced ideas like photoelectrochemical methods, trying to use sunlight directly to split water, mimicking photosynthesis in a way.
Very cool. Okay, from the chameleon hydrogen, let's move through the main group elements. Groups 1, 2, and then 13 through 18. The book talks about patterns, but also exceptions.
That's the theme, yeah. You see clear trends as you go down a group or across a period, but the lightest members often do their own thing. Specifically, lithium in group 1 and beryllium in group 2 show markedly atypical behavior.
How so? Different from the rest of their families.
Definitely. Lithium, for example, reacts directly with nitrogen, which other alkali metals don't typically do. Beryllium compounds are much more covalent than ionic, Unlike magnesium or calcium compounds, it's down to their tiny size and high charge density.
Right, pulling electrons strongly. And isn't there that diagonal relationship thing?
Spot on. They show similarities to the element diagonally below and to the right. Lithium resembles magnesium in some ways, and beryllium resembles aluminum.
So B acts a bit like Al.
Yeah, leading to more covalent character, amphoteric oxides, reacting with both acids and bases, things you wouldn't necessarily expect just looking straight down group 2.
Interesting. Okay, shifting over to the P block proper, groups 13 to 18, what are some highlights there?
Well, Lewis acidity is a big one, especially for lighter group 13 elements like boron. Boron trihalides, BF3, BCl3. They're classic Lewis acids because the boron only has 6 valence electrons, leaving an empty orbital ready to accept an electron pair.
Hungry for electrons.
Very. And then you have allotropes again, spectacularly shown by carbon.
Diamond and graphite.
The classic example, diamond, rigid 3D network, tetrahedral bonding, super hard, insulator. Graphite, layered structure, hexagonal sheets, conducts electricity within the sheets, slippery because the layers slide easily.
Totally different properties from the exact same element, just arranged differently.
It's a fantastic illustration of structure determining function. Sulfur is another element with many allotropes forming various rings and chains.
And what about bonding trends? The book mentions weak single bonds in period 2.
Yes. Single bonds between period 2 elements like NN or OO are often surprisingly weak.
Why is that?
It's often explained by the proximity of lone pairs. These small atoms bring their lone electron pairs very close together, causing repulsion that weakens the sigma bond between them.
Steric clash, almost, but with electrons.
Kind of, yeah. It's less of an issue for larger atoms like phosphorus or sulfur lower down, where the PP or SS single bonds are stronger because lone pairs are further apart.
Got it. And these groups are also rich in oxoacids and oxoanions.
Incredibly so, especially groups 15, 16, 17. Think nitric acid, sulfuric acid, phosphoric acid, perchloric acid, countless anions like sulfate, phosphate, nitrate. Their redox chemistry is really important and complex.
Okay, let's transition to the D block. Chapters 1922, variable, versatile, complex. Why that description?
Well, variable definitely refers to their wide range of oxidation states. Many transition metals can easily exist in several different states. Chromium, for example, from +2 up to +6.
More options than the main groups.
Way more options. Also, the heavier ones, the 4 and 5B series, often show higher coordination numbers. They can bond to more surrounding ligands than the lighter 3 metals, and high oxidation state compounds tend to be more covalent.
Right, the highly charged metal pulls electrons strongly. How do we even begin to understand all this behavior, especially their colors?
That's where advanced techniques come in, like spectroscopy. Chapter 20 dives into UV visible spectroscopy. It probes the electronic transitions within the d orbitals.
Okay.
This helps us understand concepts like ligand field splitting. The ligands around the metal create an electric field that splits the d orbitals into different energy levels.
And the energy difference corresponds to absorbed light, hence color.
Exactly. The energy gap often falls in the visible region, so the compound absorbs certain colors and appears as the complementary color. It also explains magnetic properties.
Fascinating. It's like looking inside the electron structure. What about how they react? Kinetics and mechanisms.
Chapter 21 covers that, how fast reactions happen and the pathways they take. It introduces basic mechanisms, dissociative, ligand leaves first, associative, new ligand attaches first, interchange, sort of simultaneous.
Okay.
And concepts like the trans affect how one ligand can influence the rate at which the ligand opposite to it gets substituted, crucial for synthesis. And the Marcus equation for electron transfer, considering the energy needed to reorganize molecules during the transfer.
Wow, getting quite detailed there. And chapter 22, organometallics.
Yes, the really exciting world of middle carbon bonds, crucial for catalysis. A key guiding principle here is the 18-electron rule.
Like the octet rule, but for transition metals.
Kind of, yeah. Stable organometallic complexes often achieve a total of 18 valence electrons. Metal electrons plus electrons donated by ligands. It's a useful predictor, though there are plenty of exceptions.
And weird bonding modes.
Definitely. The book talks about eta bonding, specifying how many atoms of a ligand are attached. The classic is ferrocene, the sandwich compound.
Iron between two rings.
Exactly. An iron atom sandwiched between 2 cyclopentadienyl rings. All 5 carbons of each ring are bonded to the iron. It's called eta-5 bonding, denoted AQ-Yo. Very different from simple MC bonds.
Cool. Okay, last stop on our tour. The F block elements, chapter 23. The inner transitioners.
Right, the lanthanoids and actinoids. The lanthanoids, LN, are mostly very electropositive metals. Their dominant chemistry is the +3 oxidation state, Ln3.
But not always +3.
Not always. You see atypical oxidation states when they can achieve a stable S0, F7, half-filled, or F14, full configuration, like cerium going to CSEO to get S0, making it a strong oxidant, or europium being stable as U with its F7 state.
And that famous lanthanide contraction.
Ah, yes. It's a steady decrease in ionic size across the series, from lanthanum to lutetium,
Why does that happen?
because the 4 electrons being added are terrible at shielding the outer electrons from the increasing nuclear charge. So the whole atom gets pulled in slightly with each step across.
And that has knock-on effects.
Huge ones. It makes the 5b elements below them very similar in size to the 40 elements above them, leading to very similar chemistry between pairs like zirconium-hafnium or niobium-tantalum, a really important consequence. And yeah, both lanthanoids and actinoids generally have high coordination numbers because they're large ions.
Okay. And the actinoids, and
These are all radioactive, which makes studying them tricky. They show a wider, more complex range of oxidation states than the lanthanoids. Uranium, for instance, goes from U with I all the way to UVI.
and the practical side.
While a key application is using volatile uranium hexafluoride, UF6, to separate uranium isotopes for nuclear fuel and weapons, using diffusion or centrifuges.
Right. So we've gone from hydrogen all the way down to the F block. A huge journey.
It really is. And the big takeaway from this whole section of the book is just how ordered inorganic chemistry is underneath the surface complexity. These recurring patterns and trends in size, energy, electron counts, bonding allow us to rationalize almost everything.
It's not just memorizing facts, but seeing the underlying logic.
Exactly.
Yeah.
Systematically describing and explaining properties using fundamental principles.
We hit on some key concepts today. The inert pair effect, allotropes, hydrogen bonding, spin correlation, the lanthanide contraction. These aren't just jargon, they're tools for understanding.
Absolutely. And thinking about how properties are so tied to position and electron configuration, it really makes you wonder, doesn't it? What other patterns or maybe anomalies are waiting out there at the edges of the known periodic table or under extreme conditions we haven't explored yet?
That is a fantastic thought to end on. What undiscovered chemistry is still out there? Well, thank you so much for joining us on this deep dive into the elements and their compounds.
It's been a pleasure.
It really has. It's been great guiding you through this rich tapestry of inorganic chemistry. From the Last Minute Lecture team, thanks for listening.